Imagine cooling your home without electricity, no compressor, no refrigerant, just wind. For centuries, people lived comfortably in some of the hottest deserts on Earth, using tall towers called windcatchers. They weren't experimental. They weren't rare. They worked. So why did we stop building them? Was modern air conditioning simply better? Or did we abandon something surprisingly effective? Before we uncover the answer, tell me where you're watching from in the comments. I'd love to see how many climates are represented here. Because the story begins thousands of years ago, in places where surviving summer wasn't optional. It was everything. Long before electricity reached homes, people living in some of the hottest regions on Earth faced a problem that never disappeared. Summer wasn't uncomfortable. It was dangerous. Daytime temperatures often climbed above 100 degrees Fahrenheit. Shade helped, but only for a while. Thick walls slowed the heat. They couldn't stop it. Builders needed something better. Instead of fighting the wind, they decided to use it. Somewhere in ancient Persia, more than 2,000 years ago, architects began raising tall towers above rooftops. From a distance, they looked almost like chimneys. But smoke never came out. These towers were built for something far more valuable: cool air. Today they're known as windcatchers. In Persian, they're called bavurja, which literally means wind catchers. The name wasn't poetic. It described exactly what the towers were designed to do: catch the wind. At first glance, the idea seems too simple. A tall opening faces the breeze. Air enters the tower. Somehow, the rooms below become cooler. It sounds almost impossible. But the people who built them weren't guessing. They had spent generations watching how wind moved through narrow streets, over rooftops, and around walls. They noticed patterns. Certain openings stayed cooler. Certain directions carried stronger breezes. Over time, those observations became engineering. No motors, no fans, no electricity, just careful design. As cities expanded across today's Iran and neighboring regions, windcatchers became part of everyday life. Wealthy homes had them, public buildings had them, mosques used them, even storage rooms designed to protect food relied on the same principle. The taller the tower, the better it could reach moving air above crowded streets. Some towers had one opening. Others had 4. A few had 8, allowing them to capture wind from almost any direction. That wasn't decoration. It was an adaptation. Every climate behaved differently. Builders adjusted the design to match local conditions. In places where one prevailing wind dominated, a single opening was enough. In areas where breezes shifted throughout the year, multiple openings made far more sense. Each tower reflected experience, not fashion. The remarkable part is that these structures weren't isolated inventions. Similar ideas appeared across parts of the Middle East, North Africa, and surrounding deserts. Different builders, different centuries. One shared solution: guide moving air where people need it most. Many of these buildings still stand today, not as museum displays, as functioning structures. Visitors often notice something surprising the moment they step inside. The streets outside feel scorching. The interior feels noticeably calmer, cooler, more comfortable. Nothing mechanical is running. Nothing is humming behind the walls. The building simply works. That raises an obvious question. If ancient builders could cool homes naturally in some of the harshest climates on Earth, what exactly was happening inside those towers? The answer wasn't magic. It was physics, quietly working every hour of every day. The secret wasn't hidden inside the tower. It was hidden inside the air itself. The air is always moving. Warm air rises. Cooler air sinks. Wind naturally flows from areas of higher pressure toward areas of lower pressure. Ancient builders didn't use those scientific terms. They didn't need to. They observed the results. Then they built around them. A windcatcher works because it reaches above the roofline. That's important. Near the ground, buildings, walls, and trees slow the wind. Higher up, the air moves faster and more consistently. By extending a tower into that stronger airflow, builders could capture a breeze that never reached the street below. Once the wind entered the opening, the shape of the tower did the rest. The air traveled downward through a vertical shaft. As it moved, it displaced the warmer air already inside the building. That hot air needed somewhere to go, so it escaped through other openings, or rose through another side of the tower. Fresh air entered. Hot air left. The cycle repeated itself all day. No switches, no controls, no power bill. Some windcatchers went even further. Instead of sending the air directly into a room, they guided it across an underground chamber or a shallow pool of water. The earth below the surface stays much cooler than the air above it. As the breeze passed through these underground spaces, it lost heat before reaching the living areas. Then something else happened. A small amount of water slowly evaporated. Evaporation requires energy. That energy came from the surrounding air. As a result, the moving breeze became even cooler before entering the home. It was simple. It was passive. It was remarkably effective. This combination of airflow, shade, underground cooling, and evaporation created a system that worked day after day without fuel or electricity. Every part supported the next. Remove one feature, and performance dropped. Keep them together, and the building almost behaved like a living system, constantly responding to the environment. The walls helped too. Many traditional homes were built with thick brick or adobe walls. During the day, those walls absorbed heat slowly instead of letting it rush indoors. At night, when outdoor temperatures dropped, the stored heat escaped back into the cooler air. The building cooled itself while everyone slept. By morning, the process began again. Modern engineers call this thermal mass. Ancient builders simply called it good construction. Perhaps the most surprising fact is that none of these ideas are considered outdated by science. Universities still study airflow inside windcatchers. Architects still model them using computer simulations. Engineers still measure how effectively they reduce indoor temperatures under the right conditions. The principles haven't changed. Only our buildings have. If you're enjoying uncovering forgotten engineering like this, consider subscribing. There are countless inventions that solved everyday problems long before electricity became the default answer, and many of them are still surprisingly relevant today. That raises another question. Were windcatchers merely clever for their time, or were they actually better than many people realize? The evidence suggests they were. For a long time, many people assumed windcatchers were little more than historical curiosities. Beautiful, perhaps. Clever, certainly, but no match for modern air conditioning. Then researchers began testing them. Instead of relying on stories or tradition, engineers measured airflow, indoor temperatures, humidity, and energy use. What they found surprised even experts. Under the right conditions, windcatchers could reduce indoor temperatures by several degrees without using a single watt of electricity. That may not sound dramatic, but think about it. Every degree matters when the outside temperature climbs above 100 degrees Fahrenheit. Lowering indoor temperatures naturally can reduce heat stress, improve comfort, and greatly reduce the need for mechanical cooling. And the towers never stopped working. They didn't wait for someone to press a button. They didn't depend on the electrical grid. As long as the sun heated the ground and the wind continued to move, the system remained active. That's an extraordinary level of reliability. Even more impressive was their efficiency. A modern air conditioner constantly consumes electricity while it runs. Compressors cycle on and off. Fans move air through ducts. Refrigerants absorb and release heat in a continuous mechanical process. Windcatchers needed none of that. The wind supplied the energy. Gravity helped move the air. The building itself became part of the cooling system. Instead of forcing nature to cooperate, ancient builders designed homes that cooperated with nature. That difference is easy to overlook. Modern construction often treats the building as a sealed box. If it becomes too hot, machines remove the heat. Windcatchers followed the opposite philosophy. Prevent the heat from building up in the first place. This approach is now called passive cooling. Ironically, it's considered one of the most important ideas in sustainable architecture today. Researchers have even recreated traditional windcatchers using computer models and full-scale experiments. Some designs have been adapted for schools, offices, and public buildings in regions with hot, dry climates. Not because they're old, because they still work. That doesn't mean windcatchers can replace air conditioning everywhere. Climate matters. A windcatcher performs best where hot days are paired with relatively dry air and dependable breezes. In places with high humidity or little wind, the cooling effect becomes less dramatic. Mechanical systems remain more practical in many environments. That's an important distinction. The goal isn't to claim that ancient builders solved every problem. They didn't. The remarkable part is that they solved the problems they actually faced, using the materials and knowledge available to them. Stone, brick, wood, wind. Few technologies remain useful after 2,000 years. Fewer still are being rediscovered by modern engineers. So if windcatchers were effective, inexpensive to operate, and capable of cooling buildings without electricity, another mystery begins to emerge. It wasn't performance that caused them to disappear. Something else changed. And that change reshaped the way almost every home on Earth would be built. It happened gradually. Windcatchers didn't disappear because they stopped working. They disappeared because the world changed around them. The first major shift arrived during the 20th century. Electricity spread into cities and eventually into millions of homes. For the first time, cooling no longer depended on the direction of the wind or the design of a building. It depended on a machine. Mechanical air conditioning offered something ancient systems couldn't always guarantee: consistency. With the push of a button, people could cool almost any room, almost anywhere, regardless of the building's design. It worked during calm days. It worked in dense cities. It worked in climates where traditional windcatchers struggled. That convenience changed everything. Architects no longer had to orient homes toward prevailing winds. Thick walls became less important. Courtyards grew smaller. Large glass windows became common. Buildings slowly stopped working with nature because machines could compensate for almost any design. The result was a new way of thinking. Instead of asking, how should this building stay cool? The question became, how much air conditioning should we install? That single change influenced neighborhoods, office towers, apartment blocks, and even entire cities. Modern construction also favored speed. Concrete, steel, glass. These materials allowed taller buildings and faster construction, but they often stored and transferred heat differently than traditional brick or adobe. Without passive cooling features, they became increasingly dependent on mechanical systems. Energy was relatively inexpensive. Few people questioned the trade-off. Then the 21st century arrived. Electricity prices increased in many regions. Cities experienced stronger heat waves. Buildings consumed more energy than ever before. Suddenly, architects and engineers began asking an unexpected question. Did we overlook something? Researchers returned to ancient designs with fresh eyes. Not because they wanted to recreate the past exactly, but because they wanted to understand why those buildings remained comfortable for centuries. The answers were surprisingly practical. Capture natural airflow. Reduce heat before it enters. Use shade wisely. Store coolness inside the building itself. Many of these ideas now appear in modern sustainable architecture. New buildings sometimes include ventilation towers inspired by traditional windcatchers. Others combine passive cooling with efficient air conditioning, allowing mechanical systems to run less often and consume less energy. It's not about replacing technology. It's about using it more intelligently. Perhaps that's the real lesson. The builders who created windcatchers weren't trying to invent something revolutionary. They simply understood their environment better than most people do today. Every wall, courtyard, opening, and tower served a purpose. Together, they formed a complete system rather than a collection of separate parts. That's why so many of those structures are still standing, not as forgotten monuments, as proof that effective engineering doesn't always require complex machines. Sometimes the smartest solution is the one that works quietly, using nothing more than the forces that nature provides every single day. Maybe we never really stopped using windcatchers. Maybe we're only beginning to understand them again. If you enjoyed uncovering this forgotten piece of engineering history, subscribe for more investigations into the brilliant technologies our ancestors created long before modern machines. Windcatchers remind us that great engineering doesn't always need more power. Sometimes it needs better thinking. Let me know in the comments, what forgotten invention should we uncover next? I'll see you in the next investigation.